Are you ready to change the way we power our world? Get excited because the National Ignition Facility has just made a groundbreaking achievement in the field of nuclear fusion. For the first time ever, a fusion experiment has produced more energy than was used to initiate the reaction. This is a major step towards harnessing the limitless and clean energy of fusion, the same process that powers the sun. So let's take a closer look at this exciting development and find out how it could change the future of energy as we know it. Buckle up because this is going to be a wild ride. We've all heard about the potential of nuclear fusion as a virtually limitless and clean source of energy, but achieving a sustained fusion reaction has proven to be a major challenge. That's where the National Ignition Facility comes in. The NIF is based at Lawrence Livermore National Laboratory in the United States, and it's dedicated to researching a type of fusion known as inertial confinement fusion. Lasers or other high-energy beams are used in the process to heat and compress a small ball of fuel, made up of the hydrogen isotopes deuterium and tritium, to the extreme temperatures and pressures required for fusion to occur. And here's where it gets really exciting. In a recent experiment, the NIF achieved a fusion reaction that generated more energy than was used to create it, which is being referred to as the Holy Grail of virtually limitless clean energy. And it is a massive step toward the long-term goal of achieving such energy. So what exactly is nuclear fusion? In a nutshell, it is a process in which small nuclei combine to form a heavier nucleus, releasing a large amount of energy. This is the same process that powers the sun and other stars, and it has the potential to be a virtually limitless and environmentally friendly source of energy on Earth. But how do we accomplish fusion on Earth? It's not going to be easy. Fusion reactions necessitate extremely high temperatures and pressures, similar to those found in stars and planet cores. Scientists use lasers or other high-energy beams to heat and compress a small ball of fuel made up of the hydrogen isotopes deuterium and tritium to create these conditions. When these extreme conditions are applied to the fuel, the nuclei can overcome their mutual electrostatic repulsion and fuse together, releasing a large amount of energy. One of the most difficult aspects of achieving a sustained fusion reaction is ensuring that the energy generated by the reaction exceeds the energy required to initiate and sustain the reaction. This is referred to as fusion burn or energy gain. Historically, fusion reactions required more energy to initiate and sustain than they produced, making it difficult to turn fusion into a viable power source. However, recent advances in laser and beam technology have brought us closer to achieving sustained fusion reactions with a positive energy gain. Fusion has a lot of potential as an energy source because it uses very little fuel and emits very little carbon. It also generates far less radioactive waste than traditional nuclear power, which relies on fission, the splitting of atoms to release energy. However, fusion reactions have proven difficult to control, and no previous fusion experiment produced more energy than was required to start the reaction. This is known as break-even, and it's a significant milestone that scientists have been striving for decades. You may be wondering what exactly happened at the NIF. Researchers used a laser pulse to heat a small ball of fuel and create fusion plasma in the experiment. The energy in the laser pulse was enough to boil 6 kettles of water. At NIF, the fusion plasma emitted energy in the form of energetic neutrons, with the total energy produced being 50% greater than that of the laser pulse. This is the first time that a fusion experiment has reached break-even, and it represents a significant advancement in the quest to harness fusion as a viable source of clean energy. While this is an important milestone, there's still a long way to go before we can realistically turn fusion into a power plant. For starters, we need to increase the energy gain even more. Furthermore, we need to figure out how to replicate this effect much more frequently and cheaply. So how long until we see fusion power in action? It's difficult to say for sure, but if everything falls into place, we could see it in use within the next 10 years. It's possible, however, that it will take much longer. The important thing is that the latest result shows that fusion power is actually within reach. Now let's talk a little bit about the different approaches to fusion that researchers are currently using. Inertial confinement fusion and magnetic confinement fusion are the two main approaches. Magnetic confinement fusion uses a magnetic field to keep the plasma contained and from touching the container's walls. This approach has been pursued for much longer than the inertial confinement fusion and was thought to be the closest to achieving break-even. In contrast, the NIF is focusing on inertial confinement fusion, which involves heating and compressing a small ball of fuel to the extreme temperatures and pressures required for fusion to occur. The NIF's fuel is a mix of hydrogen isotopes, deuterium and tritium. To achieve these extreme conditions, the NIF uses 192 laser beams to focus energy onto a tiny capsule inside a gold cylinder called a hologram, which contains the deuterium and tritium fuels. The lasers are directed onto the capsule's surface, heating it to tens of millions of degrees Celsius and compressing it to 100 times the density of solid lead. These conditions, which are similar to those found in the cores of stars and planets, are required for hydrogen atom fusion and the release of massive amounts of energy. So, what's next for fusion research? The NIF team is already working on ways to increase energy gain and make the process more frequent and cost-effective. They're not alone in their efforts. Researchers from all over the world are working on fusion, and it's likely that we'll see even more progress in the coming years. You might be wondering why we even need fusion energy. Unfortunately, our current energy sources such as fossil fuels are finite and have negative environmental consequences. Climate change caused by the use of fossil fuels is already wreaking havoc on our planet, with rising sea levels, more frequent and severe natural disasters, and even biodiversity loss. It is obvious that we require new and sustainable sources of energy that can meet our needs while not harming the environment. One potential solution to this problem is fusion reactions. Fusion actually has the potential to provide virtually infinite and clean energy on Earth. It has several advantages over other types of energy. For one, it releases nearly 4 million times more energy than chemical reactions such as burning of coal, oil, or gas, and 4 times as much nuclear fission reactions. As a result, fusion has the potential to provide the type of baseload energy required to power our cities and industries. Another benefit of fusion is its long-term viability. Fusion reactions necessitate the use of 2 elements, deuterium and tritium. Deuterium can be extracted from any type of water, whereas tritium is created during the fusion reaction when fusion neutrons interact with lithium. This means that fusion has the potential to provide an almost infinite supply of energy. Fusion has several advantages in addition to the potential to provide abundant, sustainable energy. It does not emit harmful toxins into the atmosphere such as carbon dioxide or other greenhouse gases. Thus, it does not contribute to climate change. Helium, an inert, non-toxic gas, is a major byproduct. Fusion also generates far less radioactive waste than traditional nuclear power, which is based on the fission process. Finally, there is a low risk of proliferation with fusion. It does not use fissile materials such as uranium or plutonium, and there are no enriched materials in fusion reactors that could be used to make nuclear weapons. As a result, fusion is a more secure option than traditional nuclear power. That is pretty much it for this video, guys. What are your thoughts on fusion energy? Let us know in the comments below. We would love to hear from you. Thanks for watching. And remember, make sure to subscribe to the channel with bell notifications on if you enjoy our content. We upload really awesome stuff which you'll certainly enjoy, so hit a like on this video, leave a comment below, and we'll see you in the next one.